welcome after such a long break. So last class we should have had the class, but unfortunately there was a power cut in Mumbai, and the power came back at around 3 o'clock. But by that time I tried to log in, but then nobody was there. So I don't think anybody would wait for an hour to for the class. But still, so we'll what we will do is we'll talk about bolts today, right? That is the plan in the class today. So bolts you would, but before I start that, I would like to kind of tell the class about the project. The project, I think, weekly meetings you have to do with your TA. And then every 2 weeks or so, we'll have presentations of the group, what we did. Maybe I think once a fortnight or once in 3 weeks is what we will do. We'll have regular presentations also, so that we can basically take stock of where you stand formally. And then the TA interactions would be basically for you to kind of be on your toes, so that you make progress every week. So that the very fact that you have a meeting would actually force you to have some progress. So I think it will instill some discipline in you having those weekly meetings. That's a very important aspect of that. So, but then we also need to have some evaluation, periodic evaluation for the project. So take the project seriously. It's 50% of your grades. Hope everybody is making progress. Have you got any questions about the project? If you have, why don't you shoot now, and then we'll take it from there. Do you have any questions about the project? Anybody? You can either you can unmute or you can type in the chat box, whichever way you feel comfortable, and then we'll start today's proceedings.
So when we were discussing with our TA, there was a doubt that what are you exactly looking for? Like, what is the relative weightage for, say, novelty or first principle calculation? So what is more important to you?
No, it depends, right? If it is, see, there are two aspects of doing anything. One is some brand new idea, and other is rigor, right? Whether you are doing things rigorously. So both will have weightage. Now, if you come up with a phenomenally very good, exciting idea, of course, that will carry weight. But then, as an engineer, right? So there's a difference between us and the IDC, right? What is the difference? Can you tell me? IDC design things, we design things. Do you know the difference between what IDC does and what we do?
Maybe the mathematical rigor.
No, so mathematical rigor, just not for the heck of it, just not for the mathematics. What I'm trying to say is we actually apply solid engineering ideas. So even if our product doesn't really look very cool, so so one thing is just the idea, right? But then how well did you analyze that idea using engineering principles is what we bring to the table. We bring to the table that, okay, if I'm using this material, why am I using this material? What is the minimum thickness required? What would be a better way to assemble it? So the sound engineering principle has to come into it. So there is a product design, and then there is an engineering design. So engineering design is basically analysis and synthesis centric. So and not to say that the ideas are not important. So if you have a fundamentally very good novel idea, that definitely carries away. That you cannot shortchange, right? You need to have that idea, and that idea that's the primary thing. So that has to be there. The next thing is engineering analysis. So both go hand in hand, right? You come up with a great idea and you don't analyze it, right? The end product is very flimsy. What good is that idea in that case? Tell me. So engineering design has to have that engineering analysis. So whatever you did was based on sound engineering principles. So it should not fail. You should be able to take fatigue, right? It should be able to basically for whatever function you have decided, that function should be met based on solid engineering analysis. Did I answer your question?
Yes, sir. Yes.
So both are important. I will not say that if you have a great idea, shortchange on the analysis. Right. So analysis has to be backed up. But if you want to make a comparison, a great idea always catches everybody's attention, right? So that is very easy to sell. Great idea is very easy to sell. On the other hand, rigor is not that easy to sell. Somebody has to go look deep into your analysis and see how you have done. So if you have a great idea, it will catch attention regardless, that you don't have to sell. But I will look I'll actually look at the report, read the report, see whether there is rigor in it or not. How well you have analyzed and synthesized. So both have a look at. But if you have a great idea, you already will benefit from it. So that goes without saying, because that attracts everybody's attention. That actually puts you right in the, I would say, spotlight, right? So that sells itself. That you don't have to worry. But everybody needs to follow it up with rigor, because ideas everybody will not get great ideas, but rigor everybody can put in, given enough time and efforts, right? Yeah. So what today we'll talk about is a bolt. Bolt is a very humble thing, so you may not think very highly of the bolt, but bolt is a very important thing. So fasteners and bolts are a very important thing. Although you may think maybe not so important thing, but let me just explain why bolt is important. So bolted joints, sorry, let me just go back. Okay. It looks like my computer is becoming slow for some reason. I don't know why. Okay. Yeah, so bolted joints. Okay. Yeah. So bolted joints are needed because you have to do field assembly. You have to do disassembly, maintenance. Yeah, looks like there is a problem. Sorry for the thing, but let me do this again. Okay, so basically bolted you need because of field assembly, disassembly, maintenance, adjustment, and we also use screws. Actually, it's not bolt, but looks like a bolt or a stud for lifting, power transmission, and linear actuation. So all these lathes which you have used in your experiments, right, in your workshop, they actually have lead screws to transform the rotary motion to a linear motion. It can also act as a linear actuator. Okay, looks like it's getting a bit slow. So one of the things is, you may think that it's not very important, but a simple Boeing 747, right, the old jumbo jet, it contains 2.5 million fasteners, just one plane, 2.5 million fasteners. And surprisingly, one of the key things in plane manufacturing is fastening on the key technologies. Reason being, most of the fastening of the fuselage is done by riveting. So bolting happens in a lot of places, but riveting is a very important thing, which is also kind of a bolted thing, but a permanent one for that matter. So just what I'm trying to say is, fastening is such an important thing. One can cost you a few dollars. So if you take those aluminum fasteners, aluminum bolts which they use in aerospace, those things can cost, just one piece can cost you $30–40, give or take. So imagine the cost of 2.5 million. So just the bolt cost, not all those bolts will not be so expensive, but just the cost of fastener in a plane will probably run into a few $100,000, maybe more, maybe millions. Okay. So we all think that a bolt is a very minor thing, but bolts, especially where you have large structures where you require assembly, disassembly, maintenance, bolts are very important. And these are significant. These are reasonably significant. You use very high quality bolts in aerospace manufacturing. Bolt manufacturing for aerospace is actually an important thing. Okay, so I just gave you some ideas that with bolts and rivets, there are 2.5 million fasteners in the jumbo jet. So basically, if you have bolted joints, what will happen is there will, if I have a bolt, right? And say let's take two conditions. In one, I have say this layer one, maybe a sheet of metal or whatever, and layer two. I make an arrangement where I weld it, right? And then I make an arrangement where I bolt it. So this is my head. Sorry, let me make a better job of it. So I have say two bolts here. What is the fundamental difference between the two? Any ideas? I weld the two layers, and somehow I compress those two layers with two fasteners. I join the layers, right? Both ways. I join either by perfectly bonding somehow. Maybe welding is not the right word, but say diffusion bonding. So I basically somehow bond the two layers. So there's perfect bonding, and there is contact by using two bolts. What is the fundamental difference between these two kinds of joints? Now, permanent and temporary is fine. Functionally, I'm asking. Agreed, it's a permanent thing. I cannot disassemble. But functionally, how different will it be? What will be the difference between one? Is there an advantage of having a perfect bonding other than assembly disassembly? I'm talking about functionality. If I have a bolt, it's right. Bolt can't take shear. It cannot take lot of shear. Agreed. That's a valid point. It can take some shear. It can take lot of shear. So fundamentally, do you think so? If I have these two perfectly bonded layers, right, and apply load, right, and if I have these two bolted joints, I apply load, right, will the deflections be different? Just to get you thinking. What will be different? What would this bolt bring into the component?
Stress concentration.
Pardon? Stress concentration, some cases, but they have fillets and radii not to have stress concentration. So the issue is it will not be as rigid. This will have some compliance. If you do perfect bonding, you have rigidity, right? If you have bolted, you will have an additional say. Basically, what you can say is that there would be the bolt will be a spring, and your panels will be another spring in parallel. So there will be a stiffness issue. There will be finite compliance because of if you were to make diffusion bonded, solid, perfect bonding, if you were to do, right, it will be generally stiffer because it will be less compliant, right? Imagine I have a thick beam and two thin beams. Let's do the thought experiment. Like you have two thin beams, although in this case it's not technically they'll still bend about the same because there is perfect contact, so still bend about the same axis. So they'll not have two different neutral axes, but still the rigidity will be lower. So there will be compliance issues. And the vibration, damping, and stability will all be affected, primarily because of stiffness, right? Because your vibration is actually a function of K, zeta, and omega n. K being stiffness. You all know that this equation, right? Mx double dot plus what? Cx dot plus Kx is equal to Ft. Sorry, let me go back. I'm sorry, it looks like this is acting up today for some reason. I don't know why it's acting up. Okay. So this is what I'm talking about. So Ft, right? Meaning how my system will vibrate, right? At what frequency, what will be the amplitudes. So basically, you will get a solution as xt here if you solve this differential equation. How is the displacement? Now this is a function of c, which is some sort of a damping function of damping, which is zeta, and k stiffness, and of course mass is also important, right? So basically, the moment the stiffness changes, your vibration, your damping, nature of damping will change. There'll be more damping in this condition, I would think, because there will be more dissipation, because there's internal friction there at the interface. And load bearing capacity also would be compromised, because now the stiffness is lower with bolts, but damping is higher, and the load bearing capacity will be lower because it will have lower stiffness. And bolts, so you have taken into account for that. You have taken into account the compliances because of bolt. And then bolted joints are needed for disassembly. So maximum benefits are obtained when they're preloaded. So you will have a preloaded bolt. That's the maximum thing. Threads can plastically deform. So one of the things which you should always remember using bolts is never reuse a bolt. Never ever reuse a bolt which has been used. That's something which you should always remember. Okay. And the assemblies, this is another thing which I think somebody pointed out, that it cannot take shear stress. Bolts can take tensile, shear, and some moment also. But bolts are designed only to take tension. So whatever we do, we want the bolts to always be in tension. So the individual bolt will always be in tension. It can take some bending, it can take some shear also, but ideally a bolt is designed not to take tension or moments, just not to take shear and moments, just tension, right? So this we no. I think I don't know why this figure got messed up. This should have been straight. Okay. What I will do is I will see if I can move it, if I can rotate it by 90 degree. Okay, looks like this will work. Okay, let me go back to this. This one, the next one also is similar, so I'll fix that as well. I think this is primarily because most of my stuff is in Mac, and then when I transfer to Windows, it starts acting up. Just bear with me for a minute. Sorry for all this trouble. So a bolt looks like this. A bolt has a head. What is this? Below the bolt head, you see the green thingy, right? What is that? Anybody? Some of you would have built things, right? You use bolts in your washer. Very good. Why do I need a washer? Very good. Why do I need a washer in the first place? Yes, very correct answer. A lot of people started firing washers. Why do I need a washer? What if I don't have a washer? Let's not have a washer. Stress concentration is one thing. Yes, it can have some stress concentration. Increase surface area, damage surface for the part, reduce friction. So in a nutshell, you are giving a lot of answers. Damage the surface of the part. So you're given 4 or 5 answers. So washer actually is reasonably useful. So what I will do is I'll actually talk about washers. So washer has multiple functions. I will actually list it out for you. As you said, you identified some of the good ones. Reduce the member of the wear of the head member. You can have lower coefficient of friction, doesn't direct contact, so it will not damage the surface of the part. Also the bolt. So all these things are there, but there are a whole bunch of advantages of washer. And you got it right. Few of them you've gotten it right. So washer just doesn't do one thing, but it has multiple functions, and it's always good to have a washer. Okay. And then you say you have the two members which you are joining, the top and the bottom one. And then you would see that there is the entire portion in lot of these bolts are not threaded. Only some portion is threaded. In some cases, you'll see all the way thread. In some cases, you'll not see all the way threads. Threads would be only in some portion and the other portion will be unthreaded. Why would they make it like that? Why would they make like that? Some portion threaded, some portion unthreaded. Why would they want to do something like that?
Because the threaded part is weak in shear.
Threaded part is weak in shear. Why would threaded part be weak in shear?
Lower cross-sectional area.
Threaded part is lower. So it's not shear. It will be also weak in tension also, right? If your cross-sectional area is small, right? So if your cross-sectional area is small, say my cross-sectional area is small, I'm applying same load. So my
The threaded part has those tips like on the surface. It has very sharp like those what do you say? Tips like valleys kind of thing. So due to that that tip is basically a crack initiation point.
Not always, because I'll show you what the geometry looks like. The geometry is very different. Typically, you don't have very sharp geometries there. So those bolts, I do understand you in your mind, bolts are very sharp. The bolts are not very sharp actually. Okay, and you'd have done. Did you do your metrology experiments for measurement of bolts, thread measurements?
No, we didn't. We didn't reach the metrology part last year.
You did not reach the metrology part, as in what? Oh, because of the lockdown, is it?
Yeah.
Okay. So that's an integral part. We actually have these measurements for the pitch diameter for the things, which I'll teach you a little bit about that. But if you would have seen in the lab, you would know what is a pitch circle. How do you measure the pitch of a screw? So those things are there in the metrology lab. And I think there is a valid thing is because one of things you've gotten it right is the diameter actually is smaller than the effective diameter in some sense, right? Because there are these grooves, right, for tightening. So effective diameter will definitely be smaller than the unthreaded portion. So I should have unthreaded as much as I can. If I am not going to screw it all the way through, right? If I have a completely threaded thing, then it's okay. Then you need that, right? If you do that. But if I am just using it to tighten the bolt in there, So there are two ways you can do it, right? The one condition, what you have is you will have a thread in the part itself and you screw it. Smaller screws, typically you do that. You tap the entire thing and then you put the screw there. So there is no bolt per se, right? But if I have a bolted joint, it doesn't make sense for me to have the threading all the way through, because ideally I would need the threads only in the bolted portion, only where I have a nut, right, in the nut portion. So I need thread in the nut portion. I don't need to thread all the way through because I know that my nut will go up till this only, right? And there are standards for every bolt. I'll show you the standards also today. So how to choose the bolt for what applications. So you will have more stiffness. Your bolts. So stiffness of this portion will be better. This portion will be more stiffer, and this will be less stiff. That's one thing. And some people actually said that there can be stress concentration and all. There may be some, but mostly the issue is the compliance is different, because what happens is my area of unthreaded, which I call it AD, is typically larger than AT, which is the threaded area. Now, how do I estimate the threaded area? Any ideas? How do I find what will be threaded area? Because this will have this kind of a profile, right? So how do I find what will be an effective area? Any ideas about that? How do I do that? Okay, trigonometry is fine. Any estimates? RMS value. Okay, so something I have to do. So typically what it is done is, I'll explain what a pitch circle diameter is. People take pitch diameter, average of pitch diameter and the minimum diameter. DM, which is the minimum diameter, and the pitch diameter divided by 2 is what people typically do to find out what will be the threaded area. Of course, this is the thread diameter, so this will be pi by 4. This. Okay, so the idea is right that you have to account for these variations. Okay, and I'll explain to you what pitch is in a little bit, but these are some of the things which you have to understand. Washer, nut, and then thread. And this can be the two things which you are joining, the two components which you are joining, T1 and T2 thickness. Okay, any questions now? So when you manufacture the threads, do you know how do you manufacture a thread? How do you make a thread? Those nuts, no, how are the bolts made? And nuts also, because nuts will have internal threads. How do you make those? What will be the process to do it? Any ideas? Forming or machining? Only two? Any other way to make it? Casting may not be a very good idea because bolts typically need to have very high strength, and as cast material doesn't really have that kind of strength. So forming is a very good idea, and forming actually is actually better if you see. So this is what I wanted to show you. This rolled threads, basically this is a forming process, thread rolling. So you see the grains are nice and along so material has deformed nicely. On the other hand, when you cut it, the grains are like this only. So this may chip off. Chipping off with a machined one may be easy, as opposed to a formed one. Formed one is much stronger. Okay. So you can either do primarily cutting or forming, which is thread rolling. You can also make not on a nut, but if you want to create a threading process, you can do tapping also, but that is for internal threads. So tapping is actually a combination of forming and machining. So how many people have tapped before? Almost anybody who would have done any student competition or anything which you have made, you would have done some tapping, right? How many people have tapped? Anybody who has tapped can explain the process of tapping? Yeah, can explain the oh, everybody has done in the first year, right? So what process is tapping? Is it a forming process or is it a machining process? If everybody has done it, then I can ask the question. What do you think it is the process? Is it a machining process or is it a forming process? What does it do? Where will it fit? Primarily, if you have to put it into one process, where will you put it? Agreed that you are trying to do this. So there is some chip formation there, right? Cutting definitely is there. So when you do it, when you tap the thing, there is a material removal, right? Of course, there will be some forming, but there is a material removal there in that process. Okay. So strength-wise, the formed threads would definitely be better. And people use steel in most of the applications, except if it is a aerospace application. In that case, people use aluminum. So functions of washer, this I asked, right? This humble washer does a lot of things. First, it acts as a spacer, and then it distributes the clamp load. So what happens is, now the clamp load, which would have come only in this portion, now it is spreaded. Somebody actually explained that also. So it actually reduces the stress, distributes the loads in clamp member. It reduces the head member wear because head is not directly in touch with the part. So head member and the part also is safe. Friction is lower. It locks the bolt into so there's a lock washer also, lock the bolts into the joint. And then there is an increased preload resolution. So there's also a wave washer which can do increased preload. So you can have a increased preload so that the bolt is under tension to begin with. So these can be the functions of washer. So washer is actually, so all these things that you see and take it for granted, right? Bolts and washers, these are real engineering components, right? Once you look at it, you'll have more appreciation for it. Okay. So now come to some definitions which I want to kind of give it to you. What definitions are there? Pitch is something called, it's basically distance between two adjacent threads. So if this thread and this thread, the thread and the next thread, what would be the difference? It's called pitch. So if you rotate once, you'll move from one thread to the other thread. That's pitch. The Americans use something very different, simply the same thing, but they call it difference. They actually use something called thread per inch, TPI, thread per inch. So there are two basic standards existing today, and it's very important because you probably don't know that there are metric threads and US threads. So if you buy anything from America, it will have it will not be, it will be quarter inch, half inch thread, quarter inch bolt, half inch bolt, and threads are also different. The standards are also different. And if you buy from India or Europe, it will have M6, M4, M3. So you should always, because a lot of these things are still in metric. A lot of things are in metric, but one place where they always use inches. Anybody can tell me? There is one place where always use inches, still people don't use metric. Any guesses? There is one place where people will today, like in India, nobody uses inches, right? We use only metric system. But even in India, there is one place, one kind of product which always is in inches only.
Fluid routings.
Fluid routings, yes. Any pipe actually. All the pipes are still sold in inches. I still don't understand why that has happened. But you see any process plant, you go to any plumber also, they'll give you all the pipings are in inches. Now the tapping they can give you in millimeters actually. So if you want connectors, you will get connectors in SI. But most of the pipes which you get, at least process piping, all the refineries you go. So all the drawings are in meters, millimeters, dimensions are millimeters. I actually worked for a consultancy company where we worked with a lot of refinery drawings and design of refineries. So all the foundation of the pump will be in millimeters or meters SI units. The flange of a pump would be in inches. The piping will be in inches. The head, the head and the flow will again be in SI, meter cube per hour and meters. So flow and head again is in SI, but the flange, the piping, always, I never understood why. I think this is something that is just legacy. They have been doing it. That's how it evolved, and it never changed. So all the flanges, all the pipings are all in still inches. I still don't understand why the reason is, but for some reason, even plumbing and process piping, everything is still in inches for some reason. So that said, inches are still used pretty. US uses for everything. They don't use M standard. They actually use US standards. But India, Europe, we use something called. I'll show you how you define those. If you go to buy a bolt in the market, what do you say? So there is M3, M6, which you probably have used. So 3 mm diameter is M3, 6 mm is M6. Quarter inch is a US notion, but there is a way to specify. How do you specify a bolt? I'll get there very soon, but then I need to first finish that. So there is either pitch or TPI. That's how you define your thing. Then there is major diameter. The largest diameter of the thread is the major diameter. The smallest diameter is the minor diameter, and the pitch diameter is actually a theoretical diameter where the gap. So if you have something like this, so basically, let me do this. Hopefully I can draw a good job. So basically it's an imaginary diameter where this and this, the gap and the tooth spacing between the tooth, this dimension, and this dimension are equal. That's what pitch diameter means. So pitch diameter is an imaginary diameter where the spacing, the tooth and the gap, the tooth spacing and the gap are equal, same width. Then there is lead L, is the distance the nut moves parallel to the screw axis when it is given one turn. Right, so that will be lead. And multiple threads are also possible. So you will have double start, single start threads also is a possibility. So you can have multiple threads as well. So these are some of the things which you need to know about the threads. Now there are two basic standards that I told about. One is called American National Unified Thread. These are called UN. So the bolts will have UN ratings. The American National Unified Thread Standard defines basic thread geometry for uniformity and interchangeability. That is called a UN. The thread will have a UN thing, and UNR for greater root radius. So here you will have larger fatigue life. If you have fatigue, then the edge radius you make it larger. And then there is metric thread, which is M series. So UN is all American National, and M is the metric thread, and MJ is the greater root radius. So UNR and MJ are equivalent, and they're very close. So if you are not very careful, right, you can it looks very similar because quarter inch is 6.25 and this is 6. So if you are not very careful, you can mix up also. So there are other standards. There is UNC standard, which is basically used for general assembly, frequent disassembly, but it's not good for, it's quick assembly and disassembly, but it's not good for vibrations. And these are the normal threads. If you go buy, you buy the UNC ones, UNC threads. Then you go ahead, you can buy something called UNF, which is fine series. These are very good for vibrations, adjustments, and these find application in automotives and aircrafts. And then there is extra fine. So extra fine are for even large shock and good for shock and large vibrations. It's a very high grade alloy material. So material they use is high grade alloy. They use for instrumentation and aircraft. These ones. Okay. Now this is how the thread profile looks. So what they will do is, if you have MJ, then they would have a larger root radius. So it is shown sharp. So let me make a disclaimer here. So it is shown that it is sharp here, but it will not be sharp. There will be some root radius here. Of course, the normal one will have low, and if you take MJ, then there will be a larger root radius. And this radii, if it's large, you will have a larger fatigue life because the stress concentrations will be lower. Okay. This is how you specify a thread. If you want to go buy a thread, you have to look for the standard. This is 1/4 inch. This is 20 TPI thread per inch. So 20 threads in 1 inch. This is 3/4 length. This is UNC. Depending upon this is the normal one. If you want UNF, the fine one, UNEF, extra fine one. This is grade 5. Grade 5 is nothing but material grade. And you want a hex head. Hex head means it will have this. It can have a hex head, and hex heads are usually hex heads will have Allen heads. So you could actually go ahead and use a Allen key there. Okay. And then if you want to see the nomenclature for metric, there is M12 or M6. The equivalent for this will be actually M6. Then you'll specify pitch instead of thread per inches. Then there is material class is ISO 4.8, which was there grade 5, and hex head. So this is how, if you want to go buy a thread, all this you have to buy a bolt, all this you have to specify. We do actually when we as a consultant, when you used to buy material for piping flanges, we used to specify everything, all the details, what material we need. And you think this is very simple to have a nut and a bolt. It's very simple. I'll tell you a funny story. I was in Mathura refinery, and there was this high pressure line, hydrogen line, and these had flanges, and these flanges were tightened by studs. You know what stud is, right? Everyone knows what a stud is. How is stud different than a bolt? Anybody? Nobody. I'm sure few of you would have seen a stud and a bolt and they would know the difference, right? At least one brave soul should know the difference between stud and bolt. Yes, thank you. Shaurya says that only thread part. So it doesn't have any head. It will have the entire thing will just have a thread, nothing else. No head. So these kind of things are used typically in flanges. Everybody knows what flange is, right? Machine design course, actually flange is also a part of that. I may not cover those flanges, but you know, when we join pipes, right? When we join pipes, so we'll have a flange to join two pipes, something like this. Can you visualize? This is the thickness of the pipe, and this is a flange. There will be other flange. Sorry, a flange like this, and there would be these studs, and there would be bolts. Oh, there will be nuts on both sides. So studs will have no heads. There will be, you'll tighten with bolts on both sides, and the flange will get tightened. There will be a gasket in between. There will be a gasket in between to seal it properly. So to basically get to the story, what happened was this was a hydrogen line, and the hydrogen was on 400 bar. For those who cannot appreciate what 400 bar is, 400 bar is crazy. and we were not able to tighten the thing properly. This bolt tightening we were not able to do properly. They actually flew a guy from Italy to tighten the bolts to the right amount of torque, because only a right amount of torque would create that kind of a sealing. If you over tighten it, then also there will be a problem because the bolts can fail. And if you under tighten it, it will not seal properly and there will be leakages. And hydrogen leakages are very, very bad because hydrogen burns without, you cannot see hydrogen burning. So you will burn even without getting noticed that something is burning you. It's so bad. So it burns almost colorless. You don't even see that there is something burning actually. Right. So hydrogen and it's almost like at that pressure it will be like a massive explosion and everything will just go for a toss. One small leak and that can create a lot of trouble. Okay. So just for tightening a bolt, they actually flew a guy from Italy, and this guy would wear orange overalls, and all he would do is take a torque wrench and tighten the bolts. Somebody flew a guy to tighten the bolts from across the world to just ensuring that the torque is proper. The torque tightening is a proper. So we got a guy, and then we got a guy with a PhD to analyze what was happening on that bolts. Okay, so you may think that bolt is a very simple thing, but the repercussions of not using the right studs or right bolts, right torque or the right tension, because these are tightened with a proper torque wrench so that adequate tension is there in the bolt. So they have to be tightened to certain level of torque. Okay. So I'm trying to just give you a humble bolt is just not humble. There's a lot of science that goes even into a bolt, right? As small a part as a bolt. We'll do some analysis. Today, I'm not going to do a lot of analysis, but the next class we'll do some analysis as well here. Okay. So just wanted to narrate you a nice story. So I was very young then. I was like 21 years old, and I see this white guy tightening bolts everywhere. It was funny for me, but I never appreciated that tightening a bolt could be such a job where a PhD and a guy specially flown to tighten the bolts. One guy to analyze, another guy to tight. Okay, so this is one table taken from our own book or the design book from Shigley. So this is the major diameter. These are the bolts which are available. So these are the design data. So you can basically see coarse pitch. The 1.6 mm dia has pitch of this. So you can basically find out what is the tensile stress area and what is the minor diameter area. So everything is actually given here. Okay. So tensile stress calculations. So if I have threaded, right, this we talked about a little bit, but the tensile stress area AT is the area of unthreaded rod with the same tensile strength as the threaded rod, right? So because we have this, if you have threads, the diameter varies, right? So I have to get an equivalent AT. So here there is AR. So this is DR. This is D max, right? And then there is pitch. And I have to find out what will be, for this kind of threaded portion, what will be an equivalent solid rod, right? Which will have an cross-sectional area of 80. And this is what you use in all the calculation. On the bolt design calculation, you use 80 for threaded portion. And this 80 is nothing but an average of BP, the pitch diameter and the minor diameter. Pitch diameter and the minor diameter, which is the smallest diameter. Okay. And the bolt heads again, I'll just show you. Usually uses nut. It's heavy duty. There is socket cop screw. These are for basically instrumentation and small precision applications. You use these kind of things. It can be accessed from top. Machine screws are smaller sizes. It will have either Phillips head or Phillips head, you know, right? The star-like kind of a thing, or slotted. Okay, and threaded all the way. So these will be threaded primarily all the way. So machine screws are something like this. There is round head, there is flat head, there is philister head, oval head, truss head, binding head. Hex head is again the one hex head. There is hex head trimmed and hex head upset. So hex heads typically have hex heads. You can use a wrench to undo it, or a if there is upsetting there, then you can use a Allen key to do that. Okay. Hex head bolts are most common in engineering applications. And the standard dimensions are there in 829 initially. You can look at it. W, which is the sort of this distance between the two opposite faces, is 1.5 times the diameter. And L is measured from below the head. So you measure the L right from here. Okay. So these are some of the characteristics of hex head bolt. Meter bolt size again, there is M5, M6, M8, M10, M12, 14, 16, 20, 24. So you don't get 22. So these are the ones which you actually get nominal sizes. So these are M6 means 6 mm bolt. So your normal diameter and the unthreaded portion will be 6. Okay. And then the W is for 5 it is 8, 1.5 times give or take. And then WH Armin, you know, and these are the dimensions for every kind of screw which you need. Okay. The length of threads LT, if you have English ones, which are the the UN kind of threads, it will have LT. The total length LT, the threaded length is 2D plus 1/4 inch. For less than 6 inches, for less than 2D plus ½ inch. And for metric, LD is 2D plus 6, 2D plus 12 to 25, depending upon what is the length of the bolt. Okay, so the threaded portion to the total portion is a function of what is the actual complete length. Okay. Okay. And then so bolt screw and so property, these are the class of material. So 4.6 is low carbon steel, 4.8 is lower medium carbon, 5.8 is also more low and medium carbon, but size ranges between 5 to 24. And then this medium carbon quench, QNT is quenched, and I don't remember. I'll look at it, but it's quench, and so it's harder. So these are for 16 to 36. Again, medium carbon QNT. And if you go to a very, this 12.9 is alloy steel. Right. So these are very expensive set of bolts. Okay. So it depends, and it will be, the head will be marked like this. So 4.6 will be really cheap. The QNT would be slightly more expensive, the 8.8 ones, and 12.9 would be really expensive. Okay, so you go buy the same looking bolt, but you can pay 10 times the price. So this probably would be more than 10 times expensive than this one. Okay, so you have to be on the lookout at what kind of bolt you are buying, and those standards tell what you're buying. So it's always, if you look at carefully, these things would be there in the bolts. These numbers would be there in the steel bolts. So this was talking about this API process piping, right? This API is American Petroleum Institute, and process piping is always in inches. That's what I told you. So basically, so if you have say 24-inch pipe, so if you have a 24-inch pipe, then the flange which you use, these are the flange dimensions. If you see, these are flange dimensions. So there can be, depending upon what kind of flange is there, 150 pounds, 300-pound flange. So these flange will be a number of bolts, and the diameter is given here. Number of bolts, number of diameters. So these are they basically for process piping. I just want to give you some feel for it, that there are certain things where you have to use, you're forced to use certain standards. Here you will always end up using American. They don't call it American, they always call it English units. But these English units are nothing but American standards. So if you go to America, they will call it English units. And English don't use those units anymore, unfortunately. Only the Americans use it. The milk is still sold in gallon. The juice is still in fluid ounces, which nobody else in the world uses. 64 fluid ounces. That's the size of their juice carton. But then this is something which everybody uses for some reason. I don't know why, but still, all the process piping is in inches. You use English standard studs and bolts. Okay. So basically, now let's come to some nuts. There is A31 in Appendix A31 is for typical specifications. In nuts, what happens is the first 3 threads are the ones which actually carry major load. You may have the entire thing screwed, but only first 3 threads actually carry load, and localized plastic strain in the first thread is likely. So there will be, the first thread will probably be deformed, and nuts like bolts should not be used for critical applications. Never, once you unscrew it, don't reuse it, especially for critical applications. Okay, so this is something which you should always remember. There is a washer-faced chamfered, washer-faced jam nut. Jam nut is actually lockset. Chamfered on both sides, jam nuts. So there are nuts, the regular nuts. There is washer-faced nuts. There is chamfered regular. There is washer-faced jam nut, and then chamfer shide jam nuts. So these are 4 kinds of nuts which you will see in the market. Okay. Now, what I will do is, when you have this thing, I'll do some formulation, but I'll leave it. Next class, we'll do some rigorous analysis. This class, let's just see the formulation. So if I have this grip length L, so tension loaded fasteners, what happens is grip length L includes everything being compressed. So this is the grip length. So grip length basically means everything that is compressed. So the compression is happening in these 2 members and the washers, including the washers. So the washer head prevents the burst from the hole from gouging into the fillet under the bolt head. Otherwise, what will happen is there will be some local gouging here. If you compress the, if you actually tighten the nuts very hard, right? So washer is a very integral thing. So whenever you use a nut, make sure to use a washer. Washer is a very scientific device actually. Okay, which actually does a lot of good things. It compresses uniformly, it reduces the stresses, and then there will be no bursts from the hole gouging into the in the bolt head also. So both ways it helps, because typically what happens, you'll actually do a drilling operation here. So there can be some bursts also. This burst can go ahead and gouge on the bolt head. Okay, so lot of advantages with washer. The washer looks very simple, very mundane, but it's a very useful device. Now you can also do cylinder head to a body. So for there, what happens is you will have a head cap screw, fasten the cylinder head to the body. Then this is a O-ring right here. O-ring basically is a seal. What it does, it actually stops the leakage with the O-ring. only part of the threaded is kind of the effective grip one. So this is one of the other ways to do it. Here, what happens is this is a screw, head cap screw. So so this will be actually this will be threaded. This will be probably threaded, and you tighten it, and then this here doesn't affect the stiffness, but it just is there for sealing. So I'll go ahead and talk a little bit about stiffness modeling here. So what happens is bolt is stretched. So basically, when you tighten it, the bolt is stretched. Members in the grips are compressed, right? These members in the grip. So bolt is, when you tighten, the bolt is under tension, and these members will be under compression. And under external load P. So if I am applying external load P, right? So because what may happen is this is an external load I'm applying. So these members, once I tighten it, they will go all sorts of loadings, right? They will see also the loading. They will see tension. They will see compression. But the worst condition, and typically with bolts, we should not worry about bending, because we don't design it for bending or moments. We typically design bolted joints only for taking tension. So tension is the worst condition. So what if I apply these external load P to stretch? A stretching load P is being applied on the members. Now, what will be the deflection? We can model something like this. We can assume this. So you can assume this, that first thing is the spring can be assumed, the actually loaded thread can be assumed that there are two springs in series. Just the bolt. One will be this. One will be till here, which is AD, and the other one is the thread portion, which is AT. Right. So this has, and if you know, so total bolt stiffness is basically 1 over KD unthreaded plus 1 over KT. How do you estimate KT? Is because I know KD is the unthreaded portion has diameter of AD, right? So if you know delta is equal to PL over AE, if you remember this. Basically, it comes from this. Sigma is equal to E epsilon. Epsilon is nothing but delta by L. So delta is the deflection which happens, and the initial length is L. And sigma is nothing but P over A. So if I have to find delta, delta will always be PL over AE. This is the deflection. Now, if I have to find the stiffness P is equal to K delta, right? So basically, I can put P as K delta times L, K delta times L divided by A times E is equal to delta. Delta gets cancelled, and stiffness will be K will be AE over L, right? That said, I know that there are two different stiffnesses because the diameters are different at different locations, right? So the first one would be, if I want to see that K is equal to, if the unthreaded portion is KD, it will be AD, and the length of the unthreaded portion LD, AD, E material is same, so this doesn't change. So AD E by LD, this is KD, and KT will be nothing but AT times E divided by LT. Agreed? Now I can find out KB is equal to KD times KT, KD plus KT, because it's in series, right? So you could see that KB, the actual bolt stiffness, is a function of AD, AT material. So basically diameter, threaded, unthreaded diameter, stiffness of the material, and the length of threaded and unthreaded. Right. All these parameters, AD, AT, LD, LT, and E. All these parameters affect the compliance. So if you put a bolt in there, this is the bolt compliance. This is the bolt stiffness. So this additional stiffness comes into the bolt will have finite stiffness, which will be there, and this will affect the over. So the structure's additional compliance, the bolt stiffness is right here. This is how you basically find the bolt stiffness. Okay, so this is where I had planned to teach. I went a little faster than what I expected. So I can take any questions if you guys have. Do you guys have any questions here? Any questions? Yeah. Any questions? Next class, I will actually talk about trying to find out the entire structural stiffness with accounting for the washer and also those stiffness of the members which you tighten using this. All that we will cover in the next class. Any questions you have about the project, about your general stuff? I'll be happy to answer now. No questions? So next class we'll talk about more of the analysis of bolts, and then maybe move on to the we'll do some problems also on the bolt design. Okay, that's the plan for next class. If you have any questions about anything, exams, mid-sem exams or whatever, I'll be happy to answer now. Any of the homeworks, exams, mid-sems. So if not, you guys are free to leave. I'll catch you on Monday. Thank you very much.
Hello, sir. Am I audible?
Yeah. You are.
Sir, what is the difference between application and studs and bolts? Like, where are studs used and where are bolts? Like, why do we prefer one over other or something?
Pardon, I didn't get you. Can you repeat it again?
Sir, studs versus bolts. So, like,
Okay.
where do we use studs and where do we use bolts, and why do we what is
Yeah.
the
It's a very good question. So basically, if you require very high torque, right, torque tightening, you may not want just a fixed head in the bolt, right? You would want to be able to tighten from both sides. You get me? So typically, the studs are used in flanges and other applications where you need torque tightening. You get me? So if you require very high level of tightening, you will use a stud. So studs are typically used for very high tightening. So you can have finite amount of torque on this side and the finite amount of torque on the other side also. So you have tightening from both sides. In bolts, one side is passive, right? You are tightening only from one side. And in studs, you have the option to tighten from both the sides. So typically, studs are invariably in very stringent applications where you require very high degree of tightening. Flanges in process industry, some applications where you want very high stiffness and almost like perfect contact between the mating surfaces. Okay.
Okay. Yes, sir. Thank you.
Any other questions you guys have?
So we actually wanted to ask a question related to our project. So can we ask that?
Sure, sure. Go ahead, go ahead. That's why I wanted to have some time for you to talk about. I wanted to do it in the beginning of the class also, but that's fine. Yeah, go ahead.
Sir, so we actually originally had the idea of making a grabber. You had suggested that there was a lack of novelty in the idea because grabber was already existing as well.
No. You got me wrong. What you were proposing was existing. If you make a very grabber which does the function in a different way, I would be very happy to do it. What I wanted from you was not that you're. I want some thought from you, right? Some genuine
Right.
need which you are addressing, or so that is why I actually said that. I'm not saying that grabber is not important. Don't get me wrong. But if you can make a
Right.
grabber which is better than what exists in the market today, I'll be all for it. Okay.
Okay, sir.
Get me what my idea was not against the grabber. If you do something that just doesn't exist, it's a novel idea, or
Right.
you're doing it differently. It's what I wanted to see. That's all I wanted to say. So I was not against grabber per se. Okay.
Sir, so we were also thinking of somewhat modifying it to include the functionality of a walking stick in the grabber itself. So, like you
Fair
can use
enough.
it.
Uh-huh. Yeah,
You can.
that's fine.
So we had one option which was like that. So walking stick plus grabber, both the functionalities. Or we also found some
So
designs.
if you ask my opinion, you know what I'll tell. What I will say is, you make a assisted device. This can be an assist device for an old person to
Right.
grab things and also do. So you don't call it a grabber. You call it
Right.
a assist device for elderly. And then
Right.
think about it from elderly perspective, that how this device can assist them in lifting stuff, daily stuff, where for which they cannot bend,
Right.
right?
Yes,
So
sir.
look from the human factors perspective.
Yes, sir.
I'm just throwing out ideas.
Yes.
I'm not saying that. So put in thought that how this will assist them and make their probably quality of life a shade better.
Yes, sir. Actually, the one we presented that day also, in that also we had put this as a use case that we want to do this for the elderly, but we'd also put some other ones. So we were looking at different functionalities. So one was a walking stick and a grabber in one. Another functionality that we found was a walking stick plus a seat, like something that we might be useful for the elderly is that they're walking, but after a distance, say they want to sit down. So it's a two-in-one walking stick, and if you like open it up, it can
That will be
act
a
as a
great idea. If you can design something really handy,
right.
that will be a very good thing, because elderly, a lot of times they would need something to relax on, to rest. So you get my idea. I think now you are hitting the point that you have to bring in some thought into the design, right?
Right, right. So, do you have any like suggestions as to which one we should do, or like what parameters should we have to
No, so
decide which
I'll
one might be
say,
better?
you want my idea. You bring your ideas. I can bounce it off. So if you can bring with some information, I'll be
Right,
happy to bounce it off.
right. So one is a grabber plus a
But
walking stick.
with some visualization, right? I would need to see
Okay,
if you're putting enough thought into at least have some embodiments, right?
understood.
This is the embodiment of this thing. At least I would want you to see whether if you are putting enough thought there or not. That is what I want from you.
Got it, sir. But then, if we do something like this, say a two-in-one functionality specifically for the elderly, that would suffice the expectations of the scores, right, of the project.
Look. Let me again go back to this. Nobody is going to fail this course, A. Okay, first thing. Second thing is the idea of design is twofold, right? One is so if you can put in some knowledge, so you have some engineering knowledge, right? So if you can put in an engineering knowledge to make something which helps the elderly, I say it's a great piece of work. Okay.
Got it. Okay, sir.
So functionality would be there, but you have to demonstrate that you use some of your engineering knowledge, right? Otherwise, so my argument would be, if we do something which doesn't really entail our engineering knowledge, then how are we different than somebody who's in 12th standard? Also with the design. Right? Design is a very broad term, right? Your design has to be backed up with solid engineering understanding. That's how I see it. And of course, what you have identified, right? It's a very valid need. If you can bring in a stick or a grabber for assist, so you have to actually say that actually demographic which I'm targeting is as elderly people who get fatigued, and this is how this product would help, right?
Got it, sir. Understood. We'll get
Yeah,
back
so if
to
you
you
want
with
to
some
have
more.
a meeting with me, just shoot me an email. I can set up something for you, so
Got
you
it.
can discuss at detail if you want.
Sure, sir. We'll let you know. Thank you.
Any other questions? If not, have a great day today and maybe the weekend, and Monday I'll bug you again. Okay, bye-bye.